Alright, so today, or now, we're going to be learning how to take the Laplace transform of some function t to some exponent n, some power n. And this is assuming that n is greater than 0. So just to jog your memory, the Laplace transform of t, as we found in an earlier video, is 1 over s squared, assuming s is greater than 0. So now back to Laplace of t to the n. So using our handy-dandy Laplace equation, the Laplace transform of t to the n is the improper integral from 0 to infinity of t to the n times e to the negative st dt. And now let's go back to integration by parts. Hey, hey. So we need to determine what a u and a v is. There we go. So let's set u equal to t to the n, because that's a nice thing and it's better to derive than integrate. So therefore u prime is equal to n times t to the n minus 1. So then that means that v prime is going to be e to the negative st, which means that integrating that v would be negative e to the negative st all over s. That works too. So now let's plug this back in. As we remember from integration by parts, what we have written currently is the integral of uv prime, and we want it in terms of uv minus the integral of u prime times v. So let's multiply u and v together. So we have u is t to the n, and v is negative e to the negative st over s. And we will eventually evaluate this from 0 to infinity. And then subtract from that the integral from 0 to infinity of n times t to the n minus 1 times the quantity negative e to the negative st over s, because this is u prime v. So now we can simplify the constant. So we'll leave what our uv to be evaluated for later. So we have, but we can take out the negative in front of the e so that it looks kind of prettier. So it's negative t to the n e to the negative st all over s, which will eventually be evaluated again from 0 to infinity. Minus, and so now we can take out the n in front of the t because it is a constant, and we get the integral from 0 to infinity of t to the n minus 1 e to the negative st dt. So now let's evaluate our uv term dt. So now let's evaluate our uv term at infinity. So at infinity, we can assume that e to the negative st goes to 0 faster than t. Actually, infinity going to n is just a confusing thing. So basically that just becomes 0. Infinity to a great power is still infinity, but infinity times 0 is still 0. 0 is more powerful than infinity. Mwaha. So then we subtract from that the entire thing evaluated at 0. So 0 to some exponent times e to the 0 would just be 0. So this is really handy. Our uv term goes to 0 entirely. So we have 0 minus 0, and it's just 0. So it's just gone. Okay. And so actually, we could have taken out another constant in the step above. So we have n over s, and because there's a negative in there, the subtraction sign becomes an addition sign, and you're left with the integral from 0 to infinity of t to the n minus 1 e to the negative st dt. And though this may not seem helpful right now, it will be in a minute. This whole term, the integral, is equivalent to the Laplace transform of t to the n minus 1. So this might help us out with a pattern later on when we're actually finding the Laplace transform of t to the n, because we can see that the Laplace transform of t to the n is dependent on the power before. So knowing that the first term, the uv term, is 0, and our second term, our integral of u prime v, is n over s times the Laplace transform of t to the n minus 1, we can say that the Laplace transform of t to the n is equal to n over s times the Laplace transform of t to the n minus 1. Now I know what you're thinking. You're saying, well, that's not what we're trying to solve for because we don't even know what the Laplace transform of t to the n minus 1 is. So to that I say we are now going to try a couple different cases. So we know that the Laplace transform of t is 1 over s squared when s is greater than 0, as we have written in the top right corner of your screen. So then if we take the Laplace transform of t squared, we can use this formula that we just got because the Laplace transform of t is equivalent to t to the n minus 1 in this case. So we can say the n in this case is 2, so we have 2 over s times the Laplace transform of t, because 2 minus 1 is 1. So that would be equal to then 2 over s times, well, we know the Laplace transform of t is 1 over s squared, so times 1 over s squared equals 2 over s cubed. So this looks interesting. Let's do another case to see what happens. When n equals 3, this means we're taking the Laplace transform of t cubed. So now n is 3, so we have 3 over s times the Laplace transform of 3 minus 2 is, no, excuse me, 3 minus 1 is 2, which is equal to 3 over s times 2, the Laplace transform of t squared, which let's write it out in not as simplified terms, but as 2 over s times 1 over s squared. So now you can see that the top, the numerator of these terms, is 3 factorial. So we have 3 times 2 times 1 over s to the 4th, 3 factorial. So that's pretty cool. Let's try this for one more value of n. So the Laplace transform of t to the 4th is equal to 4 over s times the Laplace transform of t cubed. And this is equal to 4 over s times 3 factorial over s to the 4th. Which is just 4 factorial over s to the 5th. So hopefully you can see the pattern that's coming. And hopefully you can see everything that's written on the board. So now we know that because of our pattern, the Laplace transform of t to the n is equivalent to n factorial over s to the n plus 1. And we do have to assume here that s is greater than 0, because that is an assumption we carried throughout the whole thing. So that's pretty cool. We hope you think it's cool too. See you later.